So we'll actually slowly get started. Are there any questions about the homework? Has that all been going just fine? Okay, I think that's set to be due tonight, tomorrow night? Tomorrow night? Okay. You should get that done, ideally sooner rather than later, so that you can spend the rest of the time studying. If you do encounter questions, feel free to email me or ask during office hours. I will admit that office hour questions are going to get a much faster response than email at this point. Okay? I went through about 10 lab reports over the weekend, and I still have another 10 lab reports still in my inbox for people asking me to review. Okay? So just kind of be aware of the delay time through email. We are almost done, so what we're going to spend today is kind of going over two new topics on what you could potentially see in the future, and in my opinion where the chemistry actually gets more interesting and becomes chemistry as opposed to just looking at numbers. Okay? So we'll kind of back away from numbers and look at pictures. So when you go through and deal with 151 and 152, we fully kind of address everything about the atom. In 151, you looked at quantum mechanics a little bit, quantum orbitals, where electrons existed, and then once we got into 152, we looked at the nucleus, looked at nuclear radiation, all sorts of other fun stuff like that. Okay? So when we evaluate each of these things, we could start to address different pieces. Our nucleus is held together by what particle? Probably our neutrons are really what's holding it together. Our protons are there as that elemental charge. And then what holds the atom together? Well, we get this attractive force between the electrons and the protons within our nucleus. So we get that nice attractive force. So that explains an atom. But what happens when we make a molecule? What holds individual atoms together? Okay, and this is where I think chemistry becomes a little bit more, well, becomes more interesting to me at least. And what we're evaluating there is kind of the real aspect of what I would call chemistry, as opposed to all these mathematics where it's ultimately just applied physics. We can now start to look at something about how these different atoms interact in a very loose fashion where we don't have to evaluate numbers, and we can just kind of start to evaluate how these different structures can come together. Okay? So it's looking more at almost an engineering, if you will, on the atomic level. So it's kind of neat in that respect. So what we're really concerned about when we take two atoms, say in this case sodium and chloride, what keeps those two together as a molecule? Why do they form a molecule? Okay? We could evaluate their bonding, okay, if they have a bond. If there's a bond, what does that mean? They're sharing electrons. So what we're concerned about is bringing these two atoms close enough to each other that the outer electrons on one start to interact with the nucleus on the other one. And we're getting that attractive force. So if we hit that perfect distance, we can now start to get that attractive force as opposed to the repulsive force when you start to build bonds. We can look at the different types of bonds present, which is one of the things that you go through and evaluate when you look at organic chemistry. You looked at it a little bit in 151. You get covalent, polar covalent, ionic bonds. We can then push that further into the different types of intermolecular forces. So now it's an attractive force, but it's not an actual bond. How do those things affect what we end up seeing and observing? So when we go through and look at these things, what we want to do is see the amount of sharing. Okay? If the electrons share a lot, we would expect a bond. What if they don't share as much but are still doing some kind of loose coordination? Well, then we're applying a different type of interaction. We need to be able to come up with some way to interpret that. So what different things would contribute to electrons sharing? You have already seen it before. It's a chapter that's usually glossed over in 151. What property of atoms would contribute to atoms sharing electrons? Particular bonding electrons. Could look at electronegativity. So if you have to move into organic chemistry, electronegativity becomes huge. That determines roughly 60% of the chemistry that you'll see. Right? So if you can just apply the principles of electronegativity, it's amazing how far that single process goes through and applies. Okay? So which electrons are then going to be shared? If we're going to take two nuclei or two atoms and we bring them near each other, which electrons are likely to be shared to generate that bond? Why would the outer electrons be the most likely to be shared? They're furthest on the outside. If we're going to take two things and bring them near each other, what's the first thing that's likely to interact? The middle or the outer side. Okay? If we don't like, or it's not really that we don't like the term, scientists don't like the idea of just saying outer, so we came up with another term, and that's where we get valence electrons. So it's the outer shell of electrons. Those electrons are what are contributing to bonding. So how do the individual atoms get affected by this interaction? Okay, well, depending on the different extents or the different types of sharing, we may end up generating bonds. We may end up generating different types of interactions, which is where we can get coordination chemistry. So a lot of this stuff comes back to looking at those aspects. And it's a lot more complex question than we give it credit for. And that's where a lot of the mathematics and physics comes in to chemistry, trying to describe the exact locations of these electrons and how they apply to everything else. So it gets a little bit dicey in there. Thankfully, when you move into both organic and I think even inorganic chemistry, you don't have to apply the mathematics as much. We try to come up with generalizations and rules that allow us to determine how these things interact with each other. So one of the first things that would be important to do would be come up with electron configurations. If we're going to look at how two atoms interact, and we know the outer electrons are going to be the ones interacting, we should know what outer electrons we're looking at. So we could go through and determine the electron configurations, which in theory you all did in 151, right? Super familiar, really easy. Yeah? No? Most of you don't remember. Is that what I'm getting? So when we go through and fill our electrons, we start at the 1s. So in theory, you've seen this picture before. We could go through and do these kind of downward as we fill. We started, the upper was at right-hand corner. And we fill our 1s first, then our 2s, 2p, 3s, 3p, 4s, 3d. Vaguely sound familiar? So as we go through and put these electrons in, we can start to build our orbital shells, our electron structure. As we add more electrons in, what happens to the size of the atom? It gets bigger, because we have to put those electrons further and further away from the nucleus, because those electrons, again, repel each other, which is why we have these different orbitals. So what can we do with this? Well, first off, what are our electron configurations? Say for oxygen and hydrogen. You all know how to do it, right? Start at 1s. And put 2 electrons in it. Are we at oxygen yet? How do you know we're not at oxygen? What atom would we be at? Be at helium. We added 2 electrons. We add 2 more. Where are we at? Beryllium. Add 2 more electrons. Carbon, 2 more electrons. Now we're at oxygen. As we go through and apply those to try and determine what orbitals those go in, we could have have this chart memorized, or we could remember back to what made up the periodic table. The first 2 columns sometimes are carried a very particular name. Anybody know what name is given to the first 2 columns of the periodic table? The S block. Why the S block? If we look at the electron configuration for anything in those first 2 columns, what's our valence shell? It's always S. If we look at the next section of the periodic table, so in this case what we're looking at is row 3 or column 3 to 12. What are those known as? D block, because our D electrons happen to be the last ones filled. If we look to the next section, 13 through 18, P block. Why? P orbitals happen to make up the last valence shell. So we can come up with patterns within our periodic table, and in fact, someone more intelligent than probably any of us already went through and established these extra little rules or hidden features built into this table so that we can determine and see these different things. Okay? So if we went through and evaluated, we could come up with the electron configurations for each of those atoms. For those of you thinking what kind of questions I could ask on the exam, this is a nice simple question. What are the electron configurations for any given atom? So nice and simple. Which are the electrons most relevant when we go through and look at this? For oxygen, which ones are we looking at? Ends up being not just the P, but also the S. Why the S as well, the 2S and the 2P? Those are our outermost electrons. Okay, those p electrons are a little bit further away, but as far as relative distances, they aren't that far away from the 2s. So when we look at our outermost electrons, we're going to include everything in that last row. We're looking at the 2s and the 2p. For hydrogen, which electrons do we care about? How do you know it's the 1s? That's all it's got. Make sense? So what can we go through and do for this? Well, we can now evaluate those electron configurations and try and come up with some way to describe how that structure bonds. So we could come up with a Lewis structure. If we drew out a Lewis structure, what would we draw? Theory, you might come up with something like this, right? Put 8 electrons around our center atom. Hydrogen's got its octet of 2 electrons, because that's its maximum. Oxygen's got its octet with its 8 electrons around it, and we're all nice and happy. Interesting things that come out of the Lewis structure. What does the line represent? Represents 2 electrons, and taken further, at least the way I end up drawing it and teaching it, the line also represents a bond. Okay? So that becomes relevant because if we now try and evaluate this structure, and I want to see how this molecule interacts with another molecule, which electrons are going to be the most viable to react? Probably the lone pairs and not the bonds, because the bonding electrons are already shared between 2 atoms. For those electrons to do any chemistry, we would have to remove one of the atoms, expose the electrons to the outside. Whereas if we take a look at the lone pairs, they're already exposed. There's nothing hiding one side of it. So those become a little bit more reactive, a little bit more available. So what we've started to do is now evaluate how the structure applies to the chemistry. We can take this even further. Is this a good Lewis structure for water? Like a valid way to represent its 3-dimensional structure? No, why not? When we go through and again look at Lewis structures, we don't care anything about shape, we just care about where the electrons are. We've got all of our electrons set up. And when Lewis looked at this, he said, yeah, this is fine, except there's an interesting characteristic. We just said that this pair of electrons, our lone pair, is different from our bonding pair of electrons. Why was it different? Different atoms around it. How does that affect its chemistry? Does it end up reacting the same or different? Same or different? Different. Good answer. If it interacts differently, would we expect these 2 sets of electrons to space themselves differently as well? When we're generating 3-dimensional shapes, or filling up electron orbitals, we could only put in 2 electrons into an individual orbital, and then we had to move further away. Why did we have to do that? Why don't we just jam all of those 8 electrons into the same orbital around oxygen in the exact same space? Like charges repel. If we just evaluated our overall structure here, we try to get those electrons, at least when we drew it on paper, as far away from each other as possible. So in 2 dimensions, that looks reasonable, except that when we move into 3 dimensions, we have to account for that extra dimension of space. And when we go through and now apply that extra dimension, we end up finding out that these electrons are closer than they have to be to each other. And they end up spreading away from each other into what kind of a shape? Tetrahedral. Why is that important? Well, that changes how that molecule interacts with other things, because we're now no longer looking at a flat molecule, we're looking at something that has a three-dimensional characteristic. Taken even further, that general tetrahedral shape is because those pairs of electrons all occupied as far away from each other as possible. That assumes all of those pairs of electrons have the exact same types of interactions. Do they? No. Which means what happens further? The structure is again going to change and alter so that we can adjust how those electron clouds see each other. And we end up further changing the structure into something known as what geometry? Do you remember? Bent. We have a bent shape. So typically when we draw this out on paper, we draw it in the plane with that nice little angle on it so we can see that shape a little bit better. Okay? When we go through and evaluate this, we could look at individual partial charges. Why would the partial charges become important? Wow, that's going through all sorts of fun stuff. Why do we want to evaluate partial charges? How did we build an atom? What things make an atom? Electrons, which have what charge? What else makes an atom? Protons, which have positive charge. How did we make an atom? We put those two things near each other to neutralize. Why should we evaluate partial charges when we look at a molecule? If one end of that molecule is positive, what is it going to want to interact with? A negative. What we've now done is started to predict how that molecule will interact with other molecules, which means we could start to even look at other bonding structures. How does it interact with, say, a hydrogen ion? How does it interact with another molecule? Those individual applications are what ultimately organic chemistry looks at, and what we're going to look at here in just a second, inorganic chemistry also evaluates. So it may seem ridiculously simple and it's usually glossed over, but these are the fundamentals that actually determine what you would actually need to carry through into any other chemistry class, or for that matter, biology. So when we look at individual charged species, we know those are inherently unstable, so when we've got these partial charges, and we now put them into a solution with other things, we can start to predict how they interact with each other. So for instance, if we take a look at a sodium ion, what charge is that sodium ion? Positively charged. What things are going to coordinate to it? Or what end of the water molecule is going to start to interact with it? The oxygen side, because the oxygen side is partially negative because the lone pair of electrons on it. Okay? If we go through and evaluate, say, a negatively charged species, let's see, let's find a good one here. Let's pick chloride. What charge is chloride? Negative. What part of the water molecule is going to interact with it? The hydrogen side, because our hydrogens are positive. It seems like such a simple concept, but that, when we translate it to more complex structures, ends up generating some very interesting applications. Okay? So we're always trying to strive for that neutrality. We could look at calcium ion, and we look at calcium ion, we end up with the argon state. Why do we aim for an argon state? Looks like a noble gas. Why would anything want to look like a noble gas? Why is it more stable? Full valence shell. So we're looking at different levels of neutrality. Where is it most stable? Generating those electrons where we cancel out their spin states makes it more stable. So we end up striving for that argon state. okay? Even though that generates a positive charge on our overall molecule. When we go through and look at calcium interacting with water, we could try and look at the electron clouds, and what we end up seeing is that calcium is missing electrons in its outer shell, so water can come up and start to share electrons with it. Okay, is that going to be a strong interaction or a weak interaction? Is calcium ion soluble in water? Yeah, which means if we actually formed a bond between calcium ion and water, we're now changing its structure. We can potentially change its solubility. So when we're looking at calcium ion, what we're hoping for is just a shell of water around it, meaning it stays dissolved. If we start making that bond stronger, we might start to turn it into calcium hydroxide. That's going to play around with its solubility, and we might see a precipitate form. Okay, so the level of those electron interactions makes a substantial difference. What happens if we shift to something like copper ion? Okay, copper ion's a little bit different. If we look at its electron configuration, we now shift into those d electrons. Those d electrons are actually very interesting, and they change a lot of the chemistry of the interactions that we evaluate. So typically when you go through and learn chemistry, we go through general chemistry, then organic chemistry, then biochemistry, and then if we haven't scared you away enough, you typically shift into the field of inorganic chemistry, where you go back and you evaluate the chemistry of those transition elements. Why do we save that for last? Because that's where we're looking at the interactions of d electrons. Okay, our d shell. Those d shell electrons are respond differently than the rest of the electron clouds. Okay? So we could look at the electron orbitals and say, okay, well, we could look at electron orbitals for everything else. It doesn't really necessarily change anything. But what happens if we now have water interact with this copper ion? Because now we've got those d electrons. It's not looking at an s shell or a p shell, where there really isn't much of a difference between the individual orbitals. When we shift to this system, let's say we take a copper ion. Come on, pen. We can now divide it up into individual axes. We've got a z-axis, which is coming out at you and going away from you. We've got our x-axis and y-axis in the plane of our board. And if we put our orbital shells now over the top of that, when we bring in individual water molecules, what orbital they interact with is now going to potentially change our overall appearance. What do I mean? Well, if I bring in a water molecule, oh man, let's label our axes according to what's shown. Okay, this is always fun too. You'll notice that axes are usually not very consistently labeled. Any idea why? If we take that copper molecule or that copper atom and we spin it, what happens to it? Does it still look the same? What does a copper atom represent in 3 dimensions? If we try to draw that image, what would we likely see? A sphere. If we take that sphere and rotate it, does it look any different? No. Why is that important? Well, that means that our axis labels end up being all equivalent. So depending on what we're looking at, we can change those axes for our individual purpose, which is very frustrating, but it's the way it works. If I bring in a water molecule down from the top, H2O, interact along that z-axis. Is that interaction on that axis the same for each of those orbitals? Okay, I see a shaking head. Why do you say no? Why is it not the same? What orbital is on the z-axis? Which d? If I take a look at dyz, is it on the z-axis? Is there a lobe or an electron cloud on the z-axis? No. All right, what happens when we move to dxz? Is there a lobe or a cloud on the z-axis? No. How about dxy? No. How about dx squared minus y squared? No. How about dz squared? Yes. Why does that matter? When those electrons start to overlap, what does that do to the equality of all of those orbitals? Are they now all the same? No. Which means we start to see what's known as a splitting. Individual orbitals will pick up different energy levels. Those different energy levels contribute to what we end up seeing in the overall structure. Right? This is known as crystal field theory. Right? It is in your textbook. In this case, I picked one particular configuration. What ended up happening is that we looked at the two sets of orbitals that are on those actual axes. So your z squared is on the z-axis. Your x squared and y squared are on the x and y axis. Everything else is shifted off-axis. Okay? That means those two sets of orbitals are going to have slightly different energies, which means when we go through to evaluate how that atom interacts with other molecules, we can expect to see different energy splittings. Why does this become important? The color you see of a copper solution, what color is it? Blue. Why is it blue? Because the energy gap between the dz squared orbitals and the dxy happen to be in the blue wavelength. Or sorry, red wavelength so that we can see blue. Okay? So when you think about all the colors you see of different metal solutions, we see those colors because of crystal field theory. It's the splitting of the d orbitals into those individual colors. Okay? Bit of an advanced topic, but why is it interesting? It boils down back to what we already understand about electron configurations, how those different orbitals interact with other things. Okay? So it is a huge application. It is advanced. It is a bit difficult to evaluate. So what we want to do now is consider what kinds of things we could throw on the exam. Okay? So let's go with that first question. Which orbitals are most often involved in producing colored complex ion solutions? The d orbitals. Why not any of the other orbitals? We can't get enough of a splitting between them or a difference in energy to cause the wavelength of light to be absorbed to be visible. We're really seeing that difference show up when we're looking at our d orbitals. Other questions. What are the electron configurations for some complex ions? We looked at a couple of them. Oxygen, hydrogen. Probably wouldn't ask hydrogen. Calcium, calcium ion. Copper plus 2. You should be able to come up with those electron configurations. How do we see the colors of a complex ion solution? That one's a little bit trickier. We didn't directly mention that. So it's the splitting of the d orbitals. Okay, does that mean if we see a blue solution that that energy difference between those two orbitals correlates to a blue color or a blue wavelength? No, because if it absorbed blue, what does that mean? You wouldn't see blue because it's absorbing that wavelength. Okay, so for those of you in lab, think back to the copper lab you guys just completed. That copper solution was blue. Where did it absorb light? Where was lambda max? 800 nanometers. Where is 800 nanometers as far as our visible light spectrum goes? Blue or red? That's our red wavelength. Our sample absorbed red, which means it would allow blue to be seen. If we absorb all red light, okay, that means that red contribution to our overall spectrum is no longer seen, and we end up seeing the opposite color. We end up seeing blue. Okay? Inorganic materials, if you're thinking about material science, okay, or pretty much any engineering, a lot of that comes back to understanding the different orbital shells of these electrons. How does a d electron translate through the rest of the material? You look at semiconductors, solar cells, LEDs. All of them are applying that information, what information is stored in the band gap or where the electrons exist in the outer shell of each of these atoms. Okay? Now things that I think are a little bit more interesting. If we now start to push into stronger interactions, okay, now instead of just weak sharing between d orbitals, we now can shift into a higher sharing of electrons. Okay, and in that case, what we can move into is something known as either organic chemistry or biochemistry. Both of these fields are directly related. So for those of you interested in biology, a lot of the things that you see or can explain within biology come back to organic chemistry. And it's looking at how individual atoms within that organic structure can interact with other organic molecules. Okay? So one of the most frustrating things I've ever seen is to have a biochemist tell me that organic chemistry is completely unnecessary. It's like, well, I trust nothing out of your mouth now. Okay? All of life comes back to organic molecules. An understanding of organic chemistry allows you to apply those different fields. Okay? If you choose to ignore it, that's your choice, but that's a different thing. Okay? So what we're looking at in organic and inorganic chemistry or biochemistry are how different atoms interact. There's different rules that apply to these interactions. The important aspects are listed here at the bottom. We've already talked about some of them. Electronegativity, we looked at shape. Shape is ultimately just an application of size. In organic chemistry, we come up with another term to refer to size, and that's where you hear sterics. So all we're trying to do is make things sound as complicated as possible, even though they're relatively simple. They all boil down to these same concepts. Resonance is a new one. You probably saw that a little bit in your previous classes or in 151. You see it a lot more in organic chemistry. All it really is an application of electronegativity along with your shapes and sizes. Okay, so what happens when we look at these? A lot of organic chemistry is looking at the study of individual reactions. So in a first semester class of organic chemistry, you learn 4 reactions, okay, with a slightly different spin on it. The very first one you learn, acid-base chemistry. In theory, everybody would go into organic chemistry understanding acid-base chemistry because talked about it in 151 briefly, and we spent a good solid 2 chapters of it in 152. What makes it a little bit nicer in organic chemistry? All you have to do with organic chemistry is apply the rules. There's no numbers, there's no calculations, you don't have to worry about equilibrium constants or concentrations. You just have to apply what changed. So, if we took a look at those 4 reactions that are shown up there, you should be able to tell me which one's the acid-base reaction. Which one's the acid-base reaction? Okay. The top one is our primary acid-base reaction. You may not be comfortable with the different notations in there, but you should be able to apply your rules. What is an acid? A proton donor. So in the course of that reaction, we have to see a hydrogen ion given to something else. Okay, what's a base? Proton acceptor. So in the course of the reaction, we need to see our base accept a proton. When you go through each of these reactions, there's 2 that should show up as possible acid-base reactions. The first one, and then also the third one. Except when we look at the third one, is it just the transfer of a hydrogen ion? Is something else happening in there? Yeah, what else changed? Okay, we could get fancy and call that a double bond, or we could just say, oh, a line showed up. One of the things that you'll start to notice is that as you move through organic chemistry, we tend to simplify structures. The best part about it, we simplify the periodic table. The elements that you deal with in organic chemistry, you could count on 2 hands. Okay? If you're really lucky and you can count on multiple fingers, you can probably get away with 1 hand. Okay? So what's happening? Our first reaction is an acid-base. How about the others? What's happening in the second reaction? What's changed? Okay, I'm hearing a replacement. What replaced what? We're looking at this chloride and that iodide exchanging places. Which name for our reactions would apply best to that? Substitution. What you've just done is probably one of the more advanced topics when it comes to organic chemistry that almost every organic chemist or chemistry student loses sight of and forgets by the end of the semester. Okay? Evaluate what you see. Don't get bogged down in the details. First, come up with that basic reaction. What happened in the second one? What changed? Again, it's tricky. Is the iodine attached to the structure anymore? Which is your product, left or right-hand side of that arrow? Right-hand side of the arrow. Is the iodine attached to the structure? No. How do you know that? What does a line represent? A bond. Is there a line connecting iodine to that structure? No. Is it connected to the structure anymore? No. So somehow in the course of the reaction, we've removed iodine from the structure. Which reaction seems to or name seems to best fit that? Why an elimination? We've eliminated iodine from our molecule. Okay? How about the last reaction? Any guesses what that one's called? Good process of elimination. What actually happened in the course of that reaction? We started with 2 species and we ended with 1. What does that sound like? Addition. Applying these simple fundamentals of what's happening across your reaction, which is what you should have been doing this whole semester. Trying to identify what the reaction is, how it's working. Now, when we move through into organic chemistry, you have to come up with the rules on the functionalities of why each of these individual steps are occurring. Okay? Just to bring back 152, we'll take a look at the substitution reaction. Erase. And I'm going to draw out 2 substitution reactions. Albeit sloppily. What changed in each of these reactions? What happened? Iodine substitutes for chlorine in this reaction. Okay, so what we've done is evaluated the pattern on what's changed. Now what we want to do is come up with how did that reaction occur. Okay, I told you I'd bring back 152, so here, let's go ahead and do it. Everybody's favorite section of the material. Well, second favorite maybe. Was that an oh God? Did I really hear that? Or as we look at this other one, based on this extra information, what can you tell me? I don't know, it's a trickier question. What do rates tell you? What piece of information do they tell you? Tell you how fast the reaction occurred. How did we determine a rate law? Okay, when we looked at orders, there were 2 ways that we could evaluate the orders for an individual reaction. Go back to the experimental data where we had all sorts of numbers and we could compare things. The other way to evaluate it was to When graphing is still looking at numbers, getting on the right path with thinking about elementary steps, we're looking at mechanisms. How does that reaction actually occur? Both of these are substitution reactions. Would we expect them to have the same mechanism? In general, we might say, yeah, substitution. We call it a substitution because it happens the same thing, or the same thing happens in each case. When we go through and look at these beginning to end, it looks like ultimately the same thing's changing. We are breaking that iodine and putting on a chloride, or sorry, breaking the chloride and putting on an iodide in both cases. What else has changed? Nothing. Why is the rate different? Different structures. So one of the huge applications that you pull out of organic chemistry is how does the structure affect the reaction? To determine individual reactions at first, we can look at electronegativity, okay, and something about their reactivity. Once we start looking at mechanisms, you have to evaluate individual structures. How does the structure change how that reaction occurs? Okay, and you end up having to deal with different split-offs or different branches within each of these mechanisms. Okay? So this is where I think chemistry actually gets fun, because you get to build things. Okay, your and my definition of fun may be different, but that's neither here nor there. Okay? One of the biggest things that you end up applying when you go through with organic chemistry is your acid and base definition. We looked at the Bronsted-Lowry acid-base definition. That's proton donor and a proton acceptor. We could look at the Lewis definition. We also applied the Lewis definition, and when we looked at Lewis's rules, what did we end up with? What was a Lewis acid? Why did he shift to electrons? If you pull up that previous slide where we looked at individual reactions, how many of those reactions looked at just the transfer of protons? Less than 2. Just the acid-base reaction. So if we use just the Bronsted-Lowry definition of acid-base chemistry, we can only apply that to acid-base chemistry. We can't apply that definition to anything else. So that's where Lewis came through and came up with our electron acceptor and donor. If you go back to those reactions, you can start to see how you would apply electrons being donated or accepted in the process of each of those reactions, even the acid-base reaction. So that Lewis definition works much better to apply to all chemistry and not just acid-base chemistry. Because organic chemists like to have something special, because at this point we haven't really addressed anything neat that they get, they came up and instead of using Lewis definitions, they came up with these two extra terms, nucleophiles and electrophiles. So let's break that name down. Electro sounds like electron. Phile, from the Greek word loving. Did you read something there? So we're looking at electron loving as an electrophile. If something is electron loving, what charge does it need to be? It would need to be positive so that it can accept those electrons. If it's an electrophile, it is electron loving, it is positive. Which Lewis definition matches it? It's a Lewis acid because it wants electrons. It will accept those electrons. If we look at a nucleophile, what's happening in the case of a nucleophile? It is, nucleo sounds like nucleus. Phile, again, loving, we're looking for something that is a nucleus-loving species. What can you tell me about the nucleus? What's the charge of all nuclei? Positive. Okay, so if we've got something that is a nucleophile, what charge does it need to be if it needs to attract positive charges? Negative. Which definition matches a nucleophile? A Lewis base, so that it can give up those electrons. Okay? Those two species, or names, electrophiles and nucleophiles, play a huge role in understanding what's happening within organic chemistry. All you're trying to do is find the individual reactions or individual species that apply these definitions. If you take organic chemistry at ASU, every single one of your tests is going to involve identifying your Lewis acid and your Lewis base. Okay? At least if you take Gould. Take anybody else, they may not require you to do that. Okay? Why is it so important? Well, if you find a Lewis acid, what does it need to react with? A Lewis base. So if you spend the time to learn the definition, what does that mean? Every problem thrown at you, you already have a step up over other students because you now know what has to react with what. In all organic chemistry, all you're trying to do is find the most positive atom and the most negative atom and put them close enough to each other that they can share electrons and make that new bond. Okay? So when we go through and deal with organic chemistry, a lot of it is just about trying to make and break the correct bond. Determining what that bond is requires that we know the two atoms around that new bond. All right, well, what do those atoms have to be? Either a nucleophile or an electrophile. What if you go through and you apply your definitions and you come up with two nucleophiles around a bond? Is that bond very likely to be made? No. Why not? Like charges would repel. Right? So when we go through and look at our reactions, if we can identify the acid, then we know it has to react with the base. All we've got to do is find our best base. Okay? If we can identify our nucleophile, then all we've got to do is find the most electrophilic. Okay? So it's just a question of applying those definitions again and again and again. Okay? So, exam questions. Identify the nucleophilic or electrophilic atom in some structure. Okay, so let's give you a structure. Just for the heck of it. Let's pick this structure. Let's say identify the electrophilic atom. What atom in that structure is most likely to be electrophilic? Electrophilic meant electron loving, which means it needs to be positive. What's the most positive atom in that structure? What are our atoms to choose from? Hydrogen and nitrogen. Which one's the most positive? Why is hydrogen the most positive? Hydrogen definitely comes in with a single electron. What's the difference between hydrogen and nitrogen? You could look at the electron count. What did I say at the very beginning of this organic chemistry version of this lecture? What was the most important thing to apply? Electronegativity. Which atom is more electronegative, hydrogen or nitrogen? Nitrogen. If it's more electronegative, what is it doing to the electrons in the bond between nitrogen and hydrogen? It's attracting them, right? Which means hydrogen is now losing electrons. If it loses electrons, it becomes positive. What were we looking for? The most positive atom there. There's our explanation. We have to apply the definition, and we have to understand electronegativity. Okay? What if I'd asked for nucleophilic? Ends up being the nitrogen, again through process of elimination. But why? For it to be nucleophilic, what does it need to have? What does nucleophile stand for? Nucleus loving. For it to be nucleus loving, what charge does it need to be? Negative. What things are negative? Electrons. Which atom has more electrons? Nitrogen or hydrogen? Nitrogen. All right, so we'd look at the nitrogen being more nucleophilic. Okay? Taking a step further, we look at all the electrons in there. Which is our most reactive set of electrons? The lone pair. Where's the lone pair located? You can do better than top. It's located on the nitrogen. Which atom is going to be the most nucleophilic? The nitrogen. Okay? Nucleophile will, and then we could do all sorts of fill in the blanks. You can come up with definitions. You can come up with different phrases. A nucleophile will always pair with the electron deficient atom. Deficient meaning, Mr. Dictionary? Deficient, meaning it doesn't have them. Okay? So it would need to be the most positive. Okay? A nucleophile is something that is positive loving. It's going to pair with something that is missing electrons because that generates a positive species. Okay? We won't worry about the mechanism arrows because I didn't show any of those, so don't worry about that. I will mention you have kind of vaguely seen that when we talked about acid-base chemistry, so you should be able to apply that, but that's a huge rule in organic chemistry. When we're looking at curved arrows, we always show the motion of electrons, not the motion of atoms, okay? Which is kind of counterintuitive, but that's how it works. Okay? For those of you in biochemistry, what we end up doing is taking the principles of organic chemistry and then we spin them into trying to attempt to explain the complex mechanisms that we find within life. Okay? It's an interesting branch of organic chemistry. You can find all sorts of fun applications in there. However, I don't really want to spend any time on that because that goes into a whole lot more depth than I would ever really have any time for. Even a biochemistry class takes off a bit more than I can chew, or than anyone can chew. Okay? So what does that mean? Anybody taking any of those tests, you can take biochemistry to learn about that. I won't test you on anything from biochemistry. Okay? Questions about anything we went through? What we've got is, again, just a simple application of things that you've seen already in general chemistry. General chemistry is so overwhelming with the mathematics and the numbers, you tend to lose sight of what you're doing. When we're looking at chemistry, we're looking at trying to build individual molecules and come up with theories to explain why those molecules are built as they are. Okay? Sometimes that involves the mathematics, sometimes it doesn't. Most cases it doesn't. Okay?